Alright, today we're going to talk about buoyancy. Buoyancy is a force exerted upward by fluid on an object in the fluid, because fluid pushes in all directions. So picture your boat here in the water, and again, the pressure in the liquid below, this blue line is all the liquid down here. Again, pressure pressing in all directions, to the right, to the left, upwards and down. Well, at the top of this liquid is pushing this up, and gravity is pulling it down. And of course, if gravity is stronger than the buoyancy, the object's going to sink. It's going to right to the bottom. But if buoyancy is stronger than gravity, the object will float. So the balance between those two forces, the greatest one will win. Stronger buoyancy, floating; stronger gravity, sinking. So buoyancy opposes gravity. Again, think of an ice cube in a glass of water. Ice floats because as water freezes, it expands, its volume decreases, it floats in the water. Now, let's check the three ways they can be compared between gravity and buoyancy. So if buoyancy is greater than gravity, the object floats. So on the far right here, what's red circled, the buoyancy is greater, pushing up. This block of wood is floating because there's more buoyancy than there is gravity. It floats at the top. If the buoyancy is less than gravity, like on the far left, the object sinks. There's more pull down than push up. It's going to sink. And the third and difficult option here to get this right is when they're equal. The object remains stationary. It's a very tough line to get an object to be right center of the liquid to stay there. So you want to go up or down. We'll show it to you in a simulation later. All right, so how do you calculate the buoyant force? You can actually measure the amount very easily. You take a vessel of liquid, like on the left here, this vessel's filled to the top with water, and you take your object and with a scale, then you can weigh it. That's the string goes up to a spring scale at the top. You slowly put that object in the water, and the water will pour out, excess water, into a vessel to the side. Well, the mass of this liquid over here on the right will equal the drop in the apparent weight up here on the spring scale. So if there's 2 grams of water in this side vessel, if there's 2 here, the weight difference on the scale of the object in water will be 2 units less. I'll show you that in some detail. If you go back to one of the labs we did in, I think probably September, where we had a graduated cylinder, and we put this rock into the graduated cylinder and you measured the volume. It's an easy way to measure volume of an irregular object. At the same time, we didn't really know at the time, but we can use that same method to calculate whether or not some buoyant force on an object. So when this rock is dropped into that liquid, it went up by 2 units here, it looks like. So if that object weighed 5 grams going in, it now weighs 3 because of the 2 gram loss, apparent loss, because it's floating a little bit. And anything in the pool weighs less. If you hold somebody in the pool, they're not as heavy. People float a little bit. Every object will weigh less while it's in a liquid. The way to display fluid is equal to the buoyant force on the object. So here's another example. There's 2 pictures here. So on the left-hand side, some object on a scale weighs 3 units. It's hanging in the air. You see the vessel full of liquid below. If I slowly drop that in to the liquid, as on the right, it now only weighs 1. But that vessel, the liquid in that, poured out into the side vessel, and that weight is now 2. So you take that 2 and 1, that gives you your original mass of 3. But the apparent mass of that object in the water is right now it's 1. It's almost floating. But it seemed to have an apparent loss of 2 grams of weight. This is called Archimedes' principle, and it's a buoyant force is equal to the weight of the displaced water. Again, here's an object that weighs 7 pounds, ready to go. It's above the vessel. Has a little spillway there. As the object dropped into the liquid slowly, the water will pour into the side vessel. It now weighs 4 4 pounds. It's lost some mass, some apparent mass. Well, you can be rest assured that 3 pounds of water is sitting in this vessel here. So that 3 and the 4 gets you back to the original 7. Again, it's related to density. You can take any kind of metal object. Most of us can picture metal going to water, it's going to sink like a rock. Well, you can get metal to float or anything to float if you can expand its volume, make its apparent volume larger. So if you take some metal and hammer it into a shape of a bowl to increase its volume, you'll be able to get some air inside part of that volume. Well, air is pretty light density, you can all understand that. So the overall density of the entire object will now decrease, and we can get to the point where we can get metal things. Think of a cruise ship or aircraft carrier. They're made of steel, iron. They can be, their apparent density can be reduced to the point where they actually float as well. All right, how do submarines work? Submarines have to float, they have to sink, and have to do what's in between. And they have an ingenious way to do that. To sink a submarine, they flood the ballast tanks with water. So these ballast tanks on the side, all around the submarine, they can fill with water by letting the air out, and the apparent density will sink because there's less air now in the submarine. If they need to raise the submarine to the top, they use what's called compressed air tanks. And air, as we know, is very low density. We can compress air so much that it becomes a liquid, but it's still air, and if it's released back into the atmosphere at this pressure, it'll expand to its large volume. So they can use compressed air and push that in here and pump the water out, okay, and get air in there so that the submarine can then float again. So again, to float the submarine, you put air on the outside into ballast. To sink, you fill them with water. If you want to do in between, you got to have a regulation between the amount of water and air. All right, there are 2 simulations for you to try. Please go to the next video for that.